So we were right in the middle of this discussion about confidence versus credibility. And so credible intervals are what Bayesian is constructing. Confidence intervals, by definition, are some form of a coverage interval. Okay, so if you say confidence interval, you mean that interval covers it. It has this coverage interpretation. And maybe that's good. 95% of the time I want to be a good statistician and give 95% of my clients good inferences. And that's what it means to cover. It's a statement about the process that you're following. So this really is a very a priori sort of scenario. A lot of people use that term for Bayesians, but this is an a priori statement about a process. So here's a 75% confidence interval for this Bernoulli process that we described. But I made this process a little bit funny in that the parameter that we're trying to infer, theta, is part of the realization. And so it's a shift to the realization. I want to see how these little Bernoulli draws are shifted. Okay? And I'm telling you what the probability is. So I'm not doing inference on the probability per usual, but I'm doing inference on a shift parameter. But it's still a Bernoulli model, but where the parameter shows up is in different places. We have to be aware of that. So, shift parameter, we want to learn it. So you get to observe two instances, two IID instances. So given thetas, the x's are independent of each other. They're conditionally independent. That's what I would say. The goal is to learn theta. And a typical inference is to build a confidence interval. This is a set, it's not an interval, it's disconnected. It's either this point or that point. Okay, so, but the same notion applies. Sets, intervals. And this example is constructed just to kind of highlight what confidence is and what it's not. And so this is a 75% confidence set. Now, it's a set. There are other ones. Another 75% set would be if I reported the -1. So this is really a description of a process. If I go out and I collect some large number of samples, each comprised of two IID realizations from this process, and I form these numbers depending on this condition, either x1 is equal to x2 or it's not. And I formed these and I gave them to you as my inferences. We have to think about, do we even understand what it all means? 75% of these would nail the truth. So 75% of the time I'd be telling you the truth, and it's because this happens 50% of the time. This happens 50% of the time. That covers 100% of the time, and that covers 50% of the time. That's why it's a 75% set. And so while this statement is true, this is a 75% confidence interval, and we've nailed the rate, and it achieves this rate really quickly. There's nothing funny with it. It's a very unsatisfying solution. So I'll say, while this covers 75% of the time, it's kind of unsatisfying. Not really telling you a probability in a reasonable way. You would rather say 50% chance of that, 50% chance of the other thing, or 100% if it's this. So confidence is a statement about the process. So it's not a statement about the exact conditional data that you see. It's conditioned on the data, but the probability is coming from the process. Bayesian wants to do something different. They want to construct a set that conveys their beliefs about theta. So they're going to construct a belief set. They call that credible sets. So let me just write that down. Bayesian wants a belief set. So, like what they actually believe. And if you go back to Savage's literature, he'll talk a lot about beliefs. That's how he's calibrating things. He's trying to align data and inferences with beliefs. We think the prior can be used to do that. And that's kind of cool. And so some people say that's not so cool. I have to believe something before I can go to town on this inference problem. And there's other paradigms for doing things in settings where you don't have any real beliefs. I think that might be the case here. If I don't tell you if I'm favoring large thetas over small thetas, you have no idea. But a Bayesian wants a belief set. They call these credible sets. So this is credible. These are just words. And while we know where confidence came from, it was this term that Fisher came up with, and at first people were confused by it. What did you do? You're not saying the parameters in here, you're saying the interval covers the true parameter. What does that mean? And eventually we all got indoctrinated and we all stopped asking questions because our 101 teachers would humiliate us. Say, well, if you don't get it, that's your problem. But it is kind of a peculiar sort of thing. Like, what is this coverage thing? What does it tell me? Is it saying I'm 75% sure about what theta is if I report this answer? I don't think so. So I wouldn't be 75% sure. I'd be 100% on this, and I'd be 50% on this, and I wouldn't want to blur it over hypothetical data and hypothetical realizations that I never saw. And so Bayesians use this term, credible. I don't know exactly where it comes from. And so if anybody wants to tell me where this term comes from and were they being cheeky, what's the whole premise behind it? But both of these words don't mean very much on their own. It seems like they're saying, you know, you should be sure, but they're both reluctant to say anything about probability, especially this one. Turns out this is a probability set for belief. And so there's two ingredients. For Bayesian analysis in the first place, and then it's a question of what do we do with the posterior. And so, but all Bayesians go and form a posterior distribution, and then it's a question of what you do. So the two steps are to form the posterior, and then to come up with a probabilistic set that measures a belief on where theta lives. So let's do that. So our two ingredients are prior and likelihood. Okay, so the prior, pi theta, we kind of at least entertain since this is a shift parameter. We've seen shift parameters, the mean and the normal distribution. We might want a prior that's shift invariant. That kind of makes sense. Turns out we'd be able to derive this if you're more of a, I don't like to use my sense, I like to use math, and I like to have procedures. I'll give you a procedure later on for deriving this as the flat prior. Okay? They'll have all kinds of neat properties. They go like additional properties other than this invariance property that I'm invoking. So the likelihood. And I asked you guys to think about what the likelihood was. Now I'm just going to write it down. We had kind of an exercise in, it's a little hard to think about, but we need to connect the data to the parameters. And if we write something down that doesn't have that connection and is not conveyed exactly by this process, we've made a mistake. And so as soon as I tell you the sampling mechanism, I have inherently told you what the likelihood function is. I give you sampling mechanism, and sometimes they're complicated. They're all tangled up, and there's dependencies, but these are IID cases. So sometimes you might say, I can sample for you, but I'll never show you my function. And that does happen out there. Big computer model experiments do that. Never actually show you the function and. Never let you see it. And there are mechanisms for doing Bayes when you can't actually write down the likelihood formally. Nevertheless, there's some likelihood function. Maybe you'll see a little bit of that later on in class. So the likelihood, I'm just going to tell you what it is. Just the product, as we wrote down last time, of f x1 given theta, f, and maybe I should write down these probabilities. That's what I really mean. It's these things right here. So it's just these probabilities. Change that to the same probability function. I plug this into my probability function given theta. So I'm thinking I just write down a half and a half, and I know that's not right. because no parameters are there. There's something else being conveyed about this model. This model says x can be either this or that. And when I write this down, it doesn't have that restriction built into it. There's not something restricting what theta can be or what the x's can be. And so I need to write that in. And so I'm going to write down, this is going to be a delta function that x1 was an element of theta minus 1 or theta plus 1. So I'm going to similarly write down a delta function right here. x2 is an element of theta minus 1, theta plus 1. It's the exact same thing. It's the same IID process. But now I've described the restriction to the space. And so Ben knew that had to be there. And in his mind, he's like, get it in there. And this is probably the easiest way to just shove it into the equation. Make a switch. Sometimes it's convenient to throw your switches into the exponents, play around in different ways. But characterizing the restrictions in models is usually done through a delta function. And if you're unfamiliar with these, it just means this. Delta of some statement, this is just going to be a logical statement. It's going to be either a 1 or a 0. And this is going to happen if S is true. And this is going to happen if S is false. So I'm just going to check this condition. And so this really is establishing right here the statement probability of X not equal to theta plus 1 or theta minus 1 is equal to 0. It's putting that 0 mass down there that sometimes we just write down rather reluctantly. It's like, I told you where the mass is, why do I have to tell you the other stuff? When I teach, I often forget to tell you where the zeros are. But when you encode your likelihoods, you would better be explicit about it. Delta function to the rescue. Boundary problems, things without infinite domains, OE, so delta function is in there. And so I can rewrite this right here. And also I'll notice that my likelihood was always just proportional to this. And so these halves really aren't telling me anything. So they don't really have any information right there on their own. So this is going to be proportional to two delta functions. You could characterize it as one big delta function by putting an and symbol in the logic in the middle, but I'll just product these things together, and it's exactly the same logic. So I'm going to rewrite this. I'm going to write it as a function of theta, because I like my likelihood, I like to think in terms of theta. So I'm just going to swap this condition around. And this statement is true right here if theta is an element of x1 minus 1, x1 plus 1. So I just rewrote it. Same exact function, but now I'm thinking about it as a function just of theta. So I wrote the theta down just in one place. This is a 1. When that's a 1. When that's a 0, that's a 0. And so I'm going to rewrite this one as well. Theta is an element of x2 minus 1, x2 plus 1. So my posterior distribution is a prior distribution times this. Let's just look at the likelihood real quickly. Let's just draw it out. So let me give you an example. Usually I like to just plug numbers into equations and see if it all makes sense before I start analyzing too deeply. But here's an example. Let's say true theta is equal to 4. So that's the thing I use to generate the data. And so here's one scenario. I saw x1 is equal to 3 and x2 is equal to 5. How convenient. So I saw two different draws. I got to see all the variability in the process. So the likelihood function, if you haven't already done this in your head, is just a point mass somewhere. But it looks like this. Theta is going to be an element of either 2 or 4. That's x1 minus 1 plus 1. Theta can be an element in the other delta function of this number 4 and 5. So that's 3. Oh, 6, sorry. Yeah. This goes to show I can mess up adding 1 to something. So that's what it is. And so what does this look like? If theta is a 2, this is a 1, but that's a 0. So that's a 0 when I product them together. Not likely. 0 likelihood. Can't be. When your likelihoods are zeros, that's supposed to be telling you it can't happen. So couldn't have been 2 if I saw this answer right here. And it can't be 6 either, but they both agree that it could be 4. And so that means the likelihood is just a point mass at 4. You can scale it if you want. With our prior that we put on, what we would do to this is we'd multiply this by 1, our flat prior, and then I would normalize it so that it was just between 0 and 1 and all the mass would stack on one place. So the posterior distribution, theta, x1, x2, if I use this prior right here, it's going to look like this. For this, it's going to be 1 right here. So all my mass is right there. It's telling you that you're certain. Posterior probability of theta being 4 is 1. Everything else is 0. So that's kind of nice. In the other scenario where I get something different, it gives you a fairly satisfactory answer. And I think that most frequentists would agree this is a better answer, and they might come up with procedures for deriving this, and quite intentionally not as a Bayesian. And so there is some branch of statistics called conditional frequentism. And so, and you have to condition on ancillary statistics. I'll send out a paper to you written by Jim Berger quite a number of years ago, at least 20 years ago. And it describes this whole problem right here. And it talks about conditional frequentism. And the name of the paper is, could Fisher, Jeffries, and Neyman have ever agreed? And I can answer that question in one word. Never. On anything. So, just because of their personalities. However, there is some attempt in statistics to try to make them all agree. Jim Berger's whole take is, if you follow the likelihood principle and you use objective priors, you get it all for free. So you are the conditional frequentist. Now, is that exactly true? Some people argue it's not quite so fast. But he is luring you to say, oh, to get agreement, we should all be Bayesians. But examples are contrived for reasons of exploitation. Try to get you to believe something. So again, this is just an example. But conditioning on the data is a good idea. So if I have that right here, scenario 2, then I'm going to end up having the likelihood function is going to be equal to the product of theta element of 2, 4. And the other delta function will look exactly the same because I got the same data. So I'll just square that out. 1 squared is 1, 0 squared is 0. It really does reduce just to this one delta function right here. So the likelihood looks like this. So I am conditioning on the correct ancillary statistics, sufficient statistics. I've conditioned on the whole data set, so I've conditioned on every possible statistic here. So I kind of like that. So this is going to be 2, and this is going to be 4, right here. And these can be arbitrarily high. The point is that they're the same height. And if my arrows look good, it would actually look that way. So those have the same height in my analysis. The likelihood is weighting those thetas exactly the same. So if I use the flat prior, I just apply Bayes, I'd multiply by 1, I would normalize all this to put it into a space that lives between 0 and 1, and I'd wind up with this here. 2, 4, this would be 0.5, 50%, and this would be 0.5. And that would be my answer, and I kind of like that answer. Now, what is the Bayesian going to give you? I guess they could give you 100% or these conditional intervals right here. So they give you a 50% or a 50% is how they would describe that. So they'd say conditional on this scenario because you're conditioning on everything. They would end up providing this as their inference. What you want to do with it in a decision theoretic framework, that's still up for debate. So I think this is kind of a nice thing about Bayes. It conditions on the data in a meaningful way. It's not a statement about the process, but it's a statement about the parameters given that you've seen the data. So it's a whole different interpretation. Sometimes those things can align. So going back to the normal example under the flat prior, I love it. So everybody agrees. So it's coverage, it's optimal coverage, it's also a belief statement. And so you will get these people that will tell you, well, maybe you can interpret it just as the parameter, the probability of the parameter being in there. Maybe, and I've heard people say that, and I'm always kind of like, shameful. Because sometimes that's totally not true. And this is a good example of that. And so, in the normal example, it turns out if you're doing one-sided p-values and you discuss them as probabilities of the null hypothesis, that's not such a big error, because it's almost true. If you do that same interpretation in the two-sided hypothesis testing case, and you interpret it with the Bayesian interpretation, you're making a gross error. It's made all through science, and it's going to embarrass us thoroughly in the future. And so I think misinterpreting confidence intervals is like that as well. Now, what do I prefer? Do I prefer coverage or belief? I mean, I'm just like everybody else. Can I have them both? And in some cases, the answer is no. But can I calibrate my Bayesian intervals so that it characterizes the belief and I'm trying to get shortest intervals, and I've tailored my prior so that it gives me good coverage? If I were in a repeatable scenario and I didn't have good coverage, people wouldn't like my inferences very well. And so, honestly, I do like coverage. But in scenarios where I don't have repeatability, it's not even worth asking the question. It's just, where do I believe the parameters are? So I'll tailor my Bayesian answer to either be a frequentist answer or not. And I think this is good frequentism as well, this answer and that answer. I'm going to nail the answers. I'm going to report 50% on that, 50% on that, 100% on this right here. And I'm going to be, on average, 75% of the time right. But I'm going to answer the question either I'm 100% sure or I'm 50% sure. And I think that's a better answer. And it's also frequentist.
First, I know you were writing the active function in terms of the delta functions. You said that the half doesn't matter to the group. So if, say, we have a point fitting example and the point is biased or not biased, that would not affect my likelihood? So
it doesn't look like it's appearing in the likelihood. So that's not information that's appearing in the likelihood. It's not there.
But it appears in the Bruce Lee eventually, right?
It could. And so you might need to encode that through the prior that you're using. And so, but there's not information about that, the shift behavior of it, just because of the exchangeability nature of the coin flipping. I can't tell what you've done with it. And so if you change those probabilities, that information isn't encoded. And so, but I'm just trying to tell you what the shift is. And so the likelihood tells me that information. If I were trying to, if I thought that you had big thetas, however, And you didn't use, I've seen you generate these numbers, and I know you always use these big thetas to generate them. I could encode that through the prior, but I would need wisdom about that. And so if you didn't tell me anything about that, I'll stick with the flat product. So again, a lot of levers, a lot of choices, but I think the analysis at the end of the day is pretty convincing.
And say we have a scenario where x1 and x2 are far from each other. So say x1 is equal to 1, x2 is equal to 6. And we would never get the 4, and the likelihood would be equal to 0.
If you did that, I would assume your sampling model was wrong. Because the sampling model I wrote down for you, so keep in mind everything we've done has the model in hand. So that's a little bit of a fiction.
75% model.
The theta plus 1, theta minus 1 model. Half probabilities or whatever the probabilities are, they're still only spaced out by a unit from theta. So you just changed that. You said I get to see either 1 or 6, and I would say you gave me the wrong sampling model. Now I'm totally knows. So I haven't told you what to do if I don't hand you sampling model. So again, this is a little bit of a classroom fiction. If you know the generating model, here are all the properties about it. Here's what I do with it. So if you gave me 1 and 6, I would say, what's the real, like, now I have to be a real statistician and try to build your model. And if you just gave me 2 numbers, 1 and 6, I would be really reluctant to do anything with them.
I mean, so here whenever they said that x1 is equal to 3 and x2 is equal to 5, what was the you like that? Was that based on the 75%?
No, it was based off of this. X is equal to this, equal to the probability x is equal to theta minus 1.
Oh, okay.
So I have the model in hand. If you give me data that violates my model, I haven't told you what to do. I will never do that to you in class. Here's the model, what I believe it is, and here's data that completely contradicts it, but I still want to use it. That's called being a professional. You get people that walk into your office doing this sort of stuff all the time, where it's like, no, just stop telling me what to do, I will figure it out. So you've got all these violations everywhere.
In this case, the probability interval is same as the
It could be, but I would set it up differently if I had this answer. So my answer from this, my credible interval, my credible sets would be this. Sets would be Cx1, x2, and I'll put an R right here. The credible would be x1 plus x2 over 2 if x1 was not equal to x2. And I would have this credible set right here. So just wait for it. This almost looks like the same thing. I would say this was x1 minus 1, x1, right, like this. So I would say this had probability 100%, 1. The problem is equal to 1. This I would say with probability 0.5. This one would happen with 0.5 as well. So that's what I would report back. So there's a big difference between these things. The confidence interval, the confidence set is blending over these two scenarios. So remember what the confidence set does is it entertains doing the process a bazillion times. It's giving you a confidence level for repeating the process. The Bayesian is giving you a conditional answer, a probability statement about what they think theta is, given the data you've observed. There's no blending over other experiments. Now, they could align, like in the normal case, or they could be very different in this case. And I think that there is justification in the paper that I put up from Jim Berger. He'll explain there is a way to come up with the conditional frequentist argument, come up with this, and you have to condition on the right ancillary statistic. Ancillary statistic is going to be the difference between the observations. You're going to check if it's 0 or if it's 2. That is ancillary. It doesn't have information about the parameter on its own. If I give you 0 or 2 and ask you what is theta, you don't know. So there's no information encoded in that and how you condition on this information. So some people believe ancillary statistics don't have any information, but they can. And so just not on their own about the parameter, but conditioning on them can be a good idea. And so he ends up showing you how Neyman went about constructing this. Here's the hard part. Here's the rub that they'll explain in the paper. Coming up with the correct ancillary statistic to condition on to give you the right frequentist answers, nobody knows how to do. And so if I ask you about ancillary statistics, you probably don't know much about them, and you probably don't use them very often. As a Bayesian, if I can just condition on the whole data set, I have conditioned on the correct ancillary statistics and sufficient statistics and everything else. And so I would change the probability that I answered with, 1 or 0.5, and the confidence interval is a blending over fictitious asymptotic realizations. Keep going forever, and they'll say, on average, you're 75% right. If I did run the frequentist thing and I reported this Bayesian answer, conditional on one data set, I would have probability 1 or 0.5 on my answers. And if I ended up doing this in long run frequency, I would have the 75% on average. And so this is a good frequentist answer as well. I get all that frequentism out of this answer. Now there's no guarantees out of everything I've done that I'll always get all those properties. And that's why this example is a little bit contrived. Is that I haven't done anything special to guarantee frequentist answers in my Bayesian regimen, but I happen to get them. I've shown you a couple answers like that. The Bayesians can be good frequentists. So again, what would I do? In reality, if I were in a repeatable scenario and frequency mattered, then I would build up a frequentist analysis. I'd probably do it as Bayesian. So that's kind of my point. So at least hopefully you understand confidence is a statement about the a priori process. Credibility is a conditional statement on the data. Make sense? Okay. Think about it longer. So I think Sierra came to me a couple days ago and said, I think I finally get this confidence credible stuff. So these are a little bit mind-bending. And so what they actually are and what they are not. So keep thinking about it. We'll be doing this all semester. Any other questions about this before we carry on?
So is that credible 75% or 100%? For me, it's like...
Remember, I just get x1 and x2. So I'm either going to answer this, and I would answer this with probability 1. That is what the posterior probability is. So the posterior probability under the different scenarios, not blending over asymptotic realizations that I never saw, just conditioning. My posterior distribution looks like that, probability 1, or it looks like this, probability half-half. And that's just what it is. So my answer is a conditional answer. Conditioning on the data set instead of doing asymptotic statistics is a real difference between Bayesian methods and asymptotic frequentist methods. A lot of asymptotic frequentist methods, what we've built up is kind of a, let's imagine we get to do this over and over and over again, and that's the whole conception of probability. It's repeating the process over and over and over and over again. And so if I were a frequentist statistician, and sometimes I am, and if I could do anything in the world, I would say I get to repeat the process as many times. And if I can do that, then I can kind of hone in on my answers really good. Question is what if I see only 30 samples or something like that? Does it matter that I use this paradigm that says I get to repeat the process over and over and over again? And a lot of times it does matter. And so which view of probability you're using. So the Bayesian answer is a conditional answer. It is not blending over things. So again, like p-values, just as a step back, what are they? Bless you. Probability of the observed statistic or more extreme given the null hypothesis is true. Why am I talking about probabilities of data I never saw in the first place? So again, there's this notion of repeating that gives me the probability of those things, and I'm going to use this stuff that I never saw in the first place to weigh in on my decision about the hypothesis. So again, all these methods, they kind of are like imputing like realization, saying what would happen in long-term runs. That's not uninteresting thing to do or improper thing to do. It just depends on what your scenario is. So I think this is a thought-provoking example. Keep thinking about it. This has stirred up many debates. And so people will build whole conferences around this problem and yell at each other and argue, and you have a lot to look forward to. They don't argue as much as they did when I was coming through school. So I was kind of Bayes early. And, you know, in the early 2000s, we had MCMC. It was starting to get in vogue, but not a lot of people were doing it yet. And you'd show up at conferences and people would yell at each other. Nowadays, people are like, that's interesting. How well does it predict? You know, how fast is it? You know, and they ask like questions about practicalities. Just make sure if somebody's telling you, they're giving you a good answer on average, that that averaging mechanism makes sense to you. Let's move on. How about some variance estimate stuff? So we'll do this for about 13 minutes. We'll come back next time and finish up the lecture. See how far we can get. So, variance estimation. I used to be really into Bayesian epistemology, philosophy. Now I like to solve problems and give good predictive answers. And there's a lot of stuff that's very interesting in philosophy. But really what I like about Bayes is that it gives me an inference that's conditional on the data. It also gives me a joint inference on the parameters if there's more than one. Ties together their associations using the same function that generated the data. And it regularizes the space for usually reasons of low sample sizes. And so it kind of gives some traction to the models. That's really what it is, the non-Bayesian answer, functionally what is happening. At the end of the day, I never give you the probability model either in practice. And so you have to build that. And so that changes the game completely. And so we'll talk more about that in the repercussions for things like p-values and Bayesian hypothesis testing. P-value, you could just reject your model instead of your hypothesis. Big deal. Variance estimation. So here's an example. It's going to feel a little bit contrived, but I'll explain a few things with it. X is going to come from a normal model with mean mu and variance sigma squared. And I'm going to say mu is known. So that's totally contrived. I'll tell you the center, but I won't tell you the variance. Turns out people do this all the time. So in spatial processes, the whole question is about the variability of the process. So they usually mean center everything, and ask you to estimate the variances. So maybe not so contrived. As a promise through the rest of this class, this conditional inference will be useful. When we get gift sampling, you'll be deriving these posteriors all the time. So this is a conditional on mu inference, and our goal is to learn sigma squared, variance. Now I could learn sigma. I could learn functions of sigma as long as I can get back to sigma squared. Everything's 1 to 1, I'm just as happy. Okay, so sigma squared is kind of an arbitrary parameter, first place. We don't naturally think in variances. We naturally do think, I think in means. Like, humanistically, I do think in means. But variance in terms of measures of spread, it's kind of interesting when you talk about normal distributions. It does have very interesting mathematical characterizations about spread. So it's the distance to the first inflection point, sigma. Variance to variances on each side gives me about 95% of the mass. And so, but it's kind of arbitrary that we talk about it. Question?
Excuse me, what do you mean here by arbitrary?
I mean, I could think of functions of that just as easily. So I could think of sigma. I could think of, and I'll give you one. So instead of just pondering what I mean, I'll just tell you. So consider another, I'll tell you why I've done this in a second, and Christina's going to catch this real quickly. Another parameterization. Sigma squared is equal to, I'll say, let's do this the other way, phi is equal to a function of sigma squared, and I'll let that function be inverse. So I could think of this parameter, just as arbitrarily, the inverse of variance. So when the variance is high, this thing is small. And so this has a name in statistics, it's called precision. If I tell you the precision, you can tell me the variance. If I tell you the variance, you can tell me the precision. And I'll argue with you that they're both is inherent to us as humans, and that's the arbitrary part. We just choose to talk about sigma squared. Could have chosen to talk about this other thing. I wouldn't think that it's inherent to talk about inverse means. I don't think on that scale. But variance as a measure of spread is pretty arbitrary. It's a squared error difference. When I came up through life and didn't know what squaring things were, that wasn't something that was native to me. So I think that this is mathematical characterization, and I'm just inclined to talk about that one. 1 over sigma squared. It's pretty arbitrary, though. Again, all of this is arbitrary. So I want to do inference on it. Also, I'm going to make this quite intentional. I only have one data point. So I'm not going to put an I here and get n realizations. So I want to understand where the prior is making a difference and where this one data point is making a difference. And then in the next lecture, I'll have something for you that might be a little bit surprising. But we'll butter this up and we'll do n observations soon. But let's just stick with the one. So if I want to do Bayesian inference, we need the two things. 1, prior, and 2, likelihood. The likelihood is maybe the easier one to talk about right here because I've told you the sampling distribution. So I've told you the likelihood as soon as I give you the data point. So the likelihood right here is 4 phi. I don't like to write my stuff down in terms of sigma squared. I'll tell you why in a moment. Given x, and I could write mu right here, and maybe it's beneficial to do it. This is going to be proportional to 1 over 2 pi square root. Just inclined to write down the whole thing. There's usually a sigma right here. But I've changed my definition. And so I'm going to write phi to the 1/2. Phi to the 1/2 is 1 over sigma times e to the minus phi over 2 x minus mu squared. So there's usually a sigma squared right there, but I've inverted it and called it phi. So that looks just like a normal distribution. We write that bigger. Likelihood of phi given x and mu is proportional to, I'll get rid of the square root 2 pi, phi half e to the minus phi over 2 x minus mu squared. If you prefer the talk in terms of sigma squared, you could do that just as arbitrarily. I could have written this down in terms of sigma squared. This would look like 1 over sigma. So I'll just make note of that. 1 over sigma. And this thing right here, 1 over sigma squared. I'm just substituting. Am I at liberty to just change my parameterization like that in a likelihood function?
Yes.
Can I just swap it around? If it's 1-to-1 and I can go back, there's positivity of this parameter right here. And so I'm only in the positive side of all of this, so it is a 1-to-1 transform. Variances are negative, never negative. So can I just do that? Let me ask you a question. If I'm in a probability distribution, let's say I have a probability distribution on some realization Z, and I want to change what I'm talking about to 1 over Z. Can I just change all the Z's in the probability model to 1 over Z? Call it something else, call it 1 over Z phi or something like that, and substitute in phi.
In that case, you need a transform, but that's not what you're doing.
That's right. So this example right here transforms. So Z comes from some model, I'll call it FZ, some distribution. If I want to talk about GZ, some transform, so I'll call this psi, maybe. G 1 to 1. Then I can't just talk about the distribution of C phi right here. I can't just plug this thing in. So you can't do this. G inverse phi. Plugging back into that function. Not fair, because I've changed the meaning of the space that it lives in. So I need to stretch that space accordingly. So I need a derivative also. Do I need to do the same thing over here with a likelihood function? The answer is no, you don't. Remember what a sampling function is. It has these numbers plugged into it. And so if my variance were 5, I'd plug it into this model right here using variance of 5. But instead of variance of 5 right here, I'd be plugging in 0.2 for phi right there, which is equivalent. It's just writing down numbers. So the sampling distribution that generated it just has these numbers plugged in. And so I'm just going to invoke my conception of this as a function over those parameters. And it's fair game just to plug them in. For doing a Bayesian analysis, I would need a prior in the transformation on that space, on the prior space. Wouldn't matter, and I'd need the Jacobian there. So you only need the Jacobian when it's a random measure, and likelihoods are not random measures. They're just functions. Okay, so I've got this thing. Here's my question to you. What's the conjugate prior? Maybe we'll just start out simple. Question. What's the conjugate prior for phi? All you have to do is stare at this thing. I need a function I can multiply by, and after I multiply through the likelihood, it preserves its functional form. It's not Poisson, so let me help you out.
Was it inverse gamma?
Hold on. So Poisson, I would have issues with that. And it would fail my first check. And so let's remember what phi is. Phi is any positive number. Poissons are counting numbers. So doesn't live in the same space. Christina said inverse gamma. And we're getting close. Turns out if I wrote it down in terms of sigma squared, it would be inverse gamma. But in terms of writing it down in phi, it turns out it's gamma is the answer. And that's the only reason that I've swapped over. I don't want to think about inverse gamma distributions. I choose to think about gamma distributions. That is an arbitrary choice. And so I've reparameterized it. And it made me reparameterize and think about my prior a little differently because I've changed the nature of the parameter. The answer is gamma. And so I've made a very typical American choice, in fact. You might think, what does this have to do with nationalism? And it does. I mean, these are arbitrary conventions, and arbitrary conventions change. So if I were in Britain right now, I would not be talking about this as a gamma distribution. I would have left it in terms of sigma squared, and I would have actually talked about a scaled inverse chi-squared distribution. And those turn out to be inverse gammas. And so you have to understand all these connections between things. It turns out all our answers, if we parameterized in a consistent sense, turn out to be equivalent to each other. So there's different ways to skin this cat. It just depends on which scale I want to live on. Now, which scale you live on does have some implications that we have to talk about. What we're going to do next time is we'll come in, we'll do this analysis with the gamma, we'll see that this thing is conjugate. I'll show you how to update those parameters and how to interpret them. And then we'll talk about some of the other arbitrary choices are that we'll never do here. All my American friends do this. All my British friends do something different. But we can understand each other. So, talk about it more, finish this analysis up, see if it makes sense, and then we're going to change the analysis to both of these things being unknown. We'll try to infer both simultaneously and understand what that looks like. That's where we start to get some real power out of this, and answers that really might start deviating from your more traditional answers. Okay, thanks you guys. See you next time.